turn on my field instructor. And when you're soldering these, you should always solder the opposite corners first, and that'll hold everything in place. That way you can make sure that everything's pressed down correctly. So solder those first, and then we'll just solder everything else up. So after using a little bit of flux remover to clean all the connections up, I have now got a Raspberry Pi Zero with the GPIO header on it, and the first board made it very easy to hold everything together. So I hope you enjoyed this quick tip. I'm going to be making a number of other quick tip videos, as well as regular tutorials on subjects that include the Raspberry Pi, Arduino, the Internet of Things, quadcopters, general electronics, and all sorts of interesting things. And the best way to find out about these new videos is just to hit the subscribe button, which you'll find below this video. And you can also visit DroneBotWorkshop.com. On my website, I've got articles where I detail everything that I do in the videos, so please check that out as well. So until next time, take care, thank you for joining me, and we'll see you again soon here at the workshop. Bye for now. Today we'll be working with the L298CAN H-Bridge motor driver. You'll learn what an H-Bridge is and how to use the inexpensive L298CAN module with an Arduino to control the speed and direction of a pair of DC motors. We'll even build a simple robot car that you can control using the joystick. So stay tuned and welcome to the workshop. Hey, welcome to the workshop. Today we're going to be working with DC motors, and we're going to be controlling them with a component called the L298CAN H-Bridge. We're going to look at how DC motors actually work, and even a tiny bit of the history, because I think that stuff's interesting. And after that, we'll discuss what an H-Bridge is, if you're not sure of that. Once we do that, we'll examine the L298CAN. The L298CAN is a really common H-Bridge module that you can use on its own or with an Arduino, and we're going to be doing both. After we do a couple of experiments with it, we're going to actually do something amusing and build a little robot car that we can control with a joystick using Arduino and L298CAN. So let's get at it. Let's take a look at DC motors. DC motors are motors that operate on direct current, as opposed to motors which operate on alternating current. The first motor was invented by a Hungarian physicist, Daniel Stanley, in 1827, and he calls this device an electromagnetic self-rotor. Interestingly enough, the self-rotor that you see pictured here was constructed in 1827 by Stanley, and today can be found in the Museum of Applied Arts in Budapest, and the device is still working 190 years after he constructed it. Now, the self-rotor wasn't a particularly practical motor. The first practical motor was invented in 1832 by a British scientist named William Sturgeon. DC motors are available in several different configurations, from tiny little motors to absolutely huge ones. Small DC motors are very inexpensive, and therefore these are ideal for hobbyists like us for all of our little contraptions. We can use DC motors to construct robot faces. They can be used to create quadcopters. They're also often used in model planes and boats, and a myriad of other applications. So how exactly does a DC motor work? Well, here you'll see a diagram of a very simple DC motor. The shaft of the motor, the part that does the rotating, is referred to as an armature. On the armature, you'll see a couple of coils of wire. These coils are connected to the commutator. That's that little copper ring at the very front of the armature that you see. The connections to the commutator are called the brushes, where the positive and negative voltage are applied. On the other side of the motor, you'll see a couple of permanent magnets arranged in opposite magnetic polarity. Now, when DC current is applied to the commutator, it sets up a magnetic field inside the coils. The coil magnets interact with the permanent magnets, causing the armature to rotate. Now, as the armature rotates, the polarity is continually reversed, causing the magnetic field to be reversed and the rotation to continue. This type of a motor is referred to as a brush motor, as opposed to a brushless motor, and this is the type of a motor that we will be experimenting with today. So let's take a look at how an H-bridge actually works. In order to simplify things, I've drawn an H-bridge using 4 switches. In real life, the switches would probably be replaced with transistors, although you could build an H-bridge with switches if you really wanted to. Now, why is this thing called an H-bridge? Well, if you look, you can distinctly see the letter H in the configuration with a motor sitting in the bridge part of the letter H, thus the term H-bridge. So how does this all work? Well, you have a positive voltage applied to the top of the H-bridge circuit and a negative voltage applied to the bottom. Now, watch what happens when we connect these two switches. The positive is applied to one side of the motor, and the negative to the other side, and in this case, our motor will spin clockwise. Now let's take a look at what happens when we close the other two switches. You will see that a negative voltage is now spin to the opposite side, causing our motor to spin counterclockwise. This is how an 80 race functions. Now, there are a couple of different styles of L298N modules that you'll run across, and I want to show you the difference between them. They work exactly the same, and you can use either of them in the experiments that we'll be doing, but I just didn't want anyone to get confused if their module didn't look like the one that I was using. So here's the one that I'm using, and you'll see all of the digital inputs with the enables on either side of this connector. Here is another common module, and here are the digital inputs. The enables are actually here, and they're jumpers, so they're always enabled, but you can just pull those jumpers and use them exactly in the same way. There's also a 5-volt jumper, which I've got off on my module is over here. The 5-volt jumper on this common module is over here. Then the motor connections, the two green connections on this module are motor A and motor B. You will find two connections on this module for motor A and motor B. And finally, the connections to the 5 volts, the 12 volts, and the ground are all done in the middle of this module here, whereas on this module, you'll find those same three connections on this connector. So otherwise, these modules are identical, and you can use either one for these experiments, and they'll work perfectly fine. Let's take a close look at the L298N module. Now, the module that you have may be physically different than the one that I'm showing here, with the connectors in a different position, but they'll be labeled the same and they'll function identically. Now, first we'll look at the power connections. There's an input for the motor power, which can be anywhere from 5 to 35 volts. There's also a common ground, which is common to all power supplies. Then there's a 5 volts input. Now, this 5 volts is to drive the logic circuitry on the board, and it's actually optional. It's possible to use the motor power to also supply the 5 volts. After that, we have two connections for our motors, motor A and motor B. Now, here's the jumper that we use to select whether we're using the optional 5-volt supply or whether we are using the internal one. In this illustration, you can see that the jumper is open. It's got it hanging there. So we are using the optional 5-volt input the way I've shown it. After that, we have the logic inputs to the control. There are 3 logic inputs for motor A, the enable line, input 1, and input 2. And then motor B has the similar connections, enable, input 3, and input 4. Now, here's how the inputs work. I'll show you motor A. Motor A's enable line, when set to 5 volts, enables the motor. When it is grounded or set to logic 0, the motor is disabled. It can also be fed pulse width modulation signals, and this can control the speed of the motor. And we'll talk about PWM in a few minutes. Now, motor A's input 1 and input 2 work as follows. If you apply 5 volts to input 1 and ground to input 2, the motor will spin in a forward direction. If you reverse that and apply ground to input 1 and 5 volts to input 2, the motor will run in reverse. And of course, the motor B inputs work in exactly the same way. Now, pulse width modulation may sound a complicated technical subject, but when it comes to controlling motors, it's actually pretty easy to understand. We simply send a series of pulses to the enable line of our motor. The wider the pulses, the faster the motor will spin. So, for example, if we send a series of short little pulses to the motor will spin slowly. If we increase the width a bit, the motor will spin faster. Increase the pulse width a bit more, and the motor will spin even faster. If we want to bring the motor to a stop, we'll just stop sending pulses and hold the enable line low. This will disable the motor. If, on the other hand, we want the motor to run at full speed, we'll stop pulsing it and hold that line high, and this will cause the motor to be enabled constantly and spin at full speed. In order to show you how the L298 works, I've set up a little experiment on the workbench. What I've done is I've taken my L298, I've removed the 5-volt jumper so that I can power this with an external supply. I've connected a power supply to it. What I've done is I've used a little buck converter that has reduced my 12-volt power supply down to 7.4 volts. Now, you might be wondering why 7.4 volts. Well, the reason for that is that the two transistors that act as switches in the L298 are each going to have a voltage drop of 0.7 of a volt. So what I need to do is apply 1.4 volts more than my motor's actually required. Since these are 6-volt motors, I've given it 7.4 volts. In addition to the 7.4 volts, I've attached a 5-volt power supply. I'm just using my bench supply for that for now. I've attached 2 motors to it, motor A and motor B, and I've also run the 5 volts over to my throttless breadboard. At this point, I've then taken all of the inputs to the L298 and wired them up to the breadboard so that I can experiment with the inputs to send them to either ground or 5 volts. Okay, for the first experiment, this is how I've wired the inputs. I've set enable 1 to 5 volts, which is a high. Input number 1 is also at 5 volts, and input number 2 is a ground. These are the lines that control motor number A. For motor B, I've taken input number 3 and set it to 5 volts. Input number 4 has been grounded, and enable number 2 has also been grounded. So when I do this, what will happen is that motor A will move forward. Motor B, however, won't move at all, and that's because its enable line is set to ground. And you can see that as follows. Okay, for the second experiment, I'm going to take enable 2, which controls motor B, and I'm going to move it high as well. In this case, both of our motors will move forward. For motor A, so I'm going to take input number 1 and ground it at input number 2 and bring it to 5 volts. This will cause motor A to run in reverse, while motor B still runs in the forward direction. And last but not least, I've taken both of the enable lines and grounded them. So enable number 1 is grounded, and so is enable number 2. In this configuration, both motors will simply be off. And as you can see, they are. So now that we've shown how the L298 works with the breadboard, let's add an Arduino to the equation and see how we can get it to control the speed of the motor as well as the direction. So let's bring in Arduino into the picture. I've taken away the 5-volt power supply, and I've used the 5 volts of ground from the Arduino Uno to power the L298N logic circuits. I've hooked the inputs of the L298N to a series of the digital outputs from the Arduino, and the hookup is as follows. I've taken the enable 1 line on the L298 and connected it to digital output pin 9 on the Arduino. Input 1 on the L298 is connected to digital output pin 8. Input 2 is connected to output pin 7. Input 3 to output pin 5. Input 4 to output pin 4. And the enable 2 line on the L298 is connected to the Arduino digital output pin 3. Again, you can use different output pins on the Arduino if you're looking to modify the sketch, but just keep in mind that both of the enable lines need to be connected to a digital output pin that is capable of pulse width modulation. So let's look at our Arduino sketch and do our motor demo. Now we're going to start off by declaring a number of integers for motor A and for motor B, and these are just the inputs for the L298N. The ENA and END are the enable lines for motors A and motor B, and then IN1, IN2, IN3, and IN4 are simply inputs 1, 2, 3, and 4 to the board. Now again, you could use different pin numbers if you wish, by just defining different numbers for these integers. However, keep in mind that enable A and enable B have to use pins that are capable of pulse width modulation. Pins 9 and pin 3 are capable of PWM, so if you're changing this, keep that in mind. After we define these integers, we're going to just go through the setup routine and set all of them up as outputs, because all of these are outputs from the Arduino, because we're feeding these into the L298Ns. Then we're going to start with one of two functions. Our first function is called Demo 1, and Demo 1 will run the motors in both directions at a fixed speed. So the first thing we're going to do is we're going to turn on motor number A with the input 1 and input 2 lines. And we're going to set the speed of motor A. We're going to be using the analog write command. Now, analog write will write pulse width modulation signals out to PWM-enabled pins of the Arduino, and it can have a range from 0, which is basically off, to 255, which is full speed. We're going to set these to analog write to 200, so it's going to be near full speed but not quite. And then we're going to do the same thing for motor B. We're going to set it on in one direction, and we're going to set it to also do an analog write of 200. Now, we're going to run the motors at that speed for 2 seconds, so we put a delay of 2,000 milliseconds in here. And then we're going to change the motor direction, so we're going to take inputs 1, 2, 3, and 4, and set them to reverse the motor, so we do that over here. And then the motor will continue to run at the speed of 200 because the analog write is still 200. We do that for 2 seconds, and then we're going to turn the motors off by setting inputs 1, 2, 3, and 4 all to a value of low. That's basically our first demo. Now we have a function for demo number 2. And what this is going to do is it's going to run the motors across all the range of possible speeds. It's going to run it up to the full speed, then run it down to low speed. So first of all, we're going to go and set the motors on again in the forward direction. So we set inputs 1, 2, 3, and 4 accordingly. And then we're going to take a loop and accelerate it from 0 to maximum speed. Now in this loop, we're going to take an integer we call I, and we're going to loop it between the values of 0 and 255. And so we're going to do an analog write to enable A and enable B. It's going to start off with these values being 0, and then we're going to delay it for 20 milliseconds. Then it's going to increment it, and the values will be 1. It'll delay for 20 milliseconds, etc., all the way until it gets up to 255. Once we do that, we're going to do the opposite thing. We're going to run a loop, except we're going to decrement it. So this is the same thing, except we're starting at a value of 255. We're working our way down to a value of 0, and we're decrementing the loop. And so again, we're going to start off with an analog write of 255 to each of the motors, delayed by 20 milliseconds, and then go to 254, delayed by 20 milliseconds, etc., until we get down to 0. And then finally, we're going to write digital writes to all of the pins low again to turn off the motors. And so now that we've defined our two functions, in a loop, all we simply do is we run demo 1, and then we delay it for a second, then we run demo 2, delay it for another second, and then the loop repeats itself infinitely. So this is basically our motor demo. So let's take a look at it working. Alright, I've loaded the motor control sketch onto my Arduino, and I've temporarily unplugged the USB cable from the Arduino because the sketch will start immediately as soon as the Arduino is powered up. Otherwise, everything's connected up. I've got my power supply connected to the L298N board, the motors are connected to it as well, and the board is connected to the Arduino. So as soon as I power this, it should start our demo sketch. So let's take a look at that. run through it. You see it'll repeat it. It starts by going forward, and goes backwards, and then it gradually comes up to speed, and then it gradually reduces speed. So that's it. Connect a couple of potentiometers or variable resistors up to the Arduino Uno. This will allow us to manually control the speed of each motor. Now, the value of each of these potentiometers is not particularly important. As long as they are 10K or higher, these should work. You also want to get linear taper potentiometers, and these are the most common type anyway. Now, one end of each pod is connected to the ground, and the other end of it connected to 5 volts. In my hookup, I used the solderless breadboard to simplify the connections, although that isn't illustrated here. The wiper of each pod is connected to one of the analog inputs on the Arduino, and I connected pod A to analog input 0, and pod B to analog input 1. Again, if you wish to use different analog inputs, that would be fine. You'll just need to modify the sketch accordingly. So now that we've hooked the 2 potentiometers up to our Arduino, let's take a look at the sketch that we're going to be using. Now, our sketch starts off in the same way as the last sketch. We define a number of integers for the output pins of the Arduino that we're using as inputs to the L298N. And we've got a couple of new integers over here, speed control 1 and speed control 2. And these are defined as A0 and A1. These represent the analog inputs in the Arduino. Now, if you wanted to use 2 of the other analog input pins, just change the value of A0 and A1, and you can do that. Now, we have another couple of integers we've defined, and these are motor speed 1 and motor speed 2, which represents the speeds of the 2 different motors. We'll initialize these with a value of 0. Then we go into the setup, which is identical to the last program. We set all of the digital outputs and define them as outputs. We don't need to set the analog inputs up as inputs because by nature they're already inputs. Then everything is happening in the loop. We'll set the motors to a forward direction by writing to the IN1, IN2, IN3, and IN4 pins. And then we're going to read the values from the potentiometers using the analog read command. Now, the analog read function uses the internal analog to digital converter that's built into the Arduino. This is a 10-bit analog to digital converter, so we're going to get values from 0 to 1023. Now, if you recall, when we do an analog write to send pulses and modulation out to our analytes, we can take a value from 0 to 255. So we've got to convert this range of 0 to 1023 to a range of 0 to 255. And there's a couple of ways we could have done this. One way would have simply been to divide these values by 4, and that would have actually worked just fine. But I chose to use Arduino's map function. And if you haven't used the map function before, it's a good function to get familiar with. What map does is it takes one range, in our case 0 to 1023, and maps it out to another range of 0 to 255. This really works well when you have 2 ranges that don't evenly divide into each other. And so I set motor speed to be mapped to a value of 0 to 255. And then the last thing I do here is I found that the motors actually started to buzz when I got to a very, very low value. And so what I've done is I simply included these if statements. And in the if statements, I say that if the motor speed is anything less than 8, then we'll just call it a 0, because the motors aren't moving down at that speed anyway. They're just making an annoying buzzing sound. You may want to adjust this value of 8 to suit your own particular motors. And then finally, we do an analog write of motor speed to enable A and enable B, and that sends the pulse width modulation out to our motors. And this is in the loop, so it just continues to repeat, read our potentiometer values, and send the values out to the 2 enable lines. And that's it for our sketch, so let's watch it in action. Okay, now that we've hooked up the 2 pots to load our sketch, let's try it out. We'll turn the pot for motor number B, and I can adjust the speed. Motor B, same thing. So now that we've seen how we can use 2 potentiometers to control 2 motors with an Arduino, let's take it a step further. Our 2 motors, you've noticed, have been mounted onto a robot car base. And what I'd like to do is actually drive this little car around the room. Now, 2 potentiometers are going to be a very difficult method of controlling a car, plus I have no method of actually reversing it. So what I've decided to do is replace the 2 pots with a joystick. Now, a joystick essentially is just 2 potentiometers, one that controls the vertical or y-axis, and the other one that controls the horizontal or x-axis. A joystick also contains a momentary contact switch, but we're not going to use that in this particular hookup. Now let's take a look at how I hook the joystick up. Essentially what I've done is just replace the potentiometers with it. A joystick also has 2 pins, one labeled VCC and one labeled ground. I've connected VCC to my 5-volt power supply from the Arduino, and I've connected the ground, of course, to the ground line. Now the vertical output I've connected to analog input A0, and the horizontal output is to analog input A1, again just the same way I had the potentiometers. Now what I've done is I've arranged the joystick so that when I push the joystick forward, the motors will drive the car forward. When I pull it backwards, the motors, of course, will drive it backwards. When I move the joystick a bit to the left, the car will steer to the left. And when I move it to the right, it'll steer to the right. As you can see over here, when I push the joystick forward, there go my motors. And when I pull it backwards, they go the other direction. If I move it out to the left, one motor shifts back